On the night of October 2nd, 2025, something appeared in the Martian sky that had no right to be there. It wasn't announced, it wasn't predicted, it simply appeared, a faint green smudge captured by the high-rise camera aboard NASA's Mars Reconnaissance Orbiter during a routine atmospheric calibration sequence. The image, time-stamped 2214 UTC, showed a diffuse glow approximately 29 million kilometers from the planet's surface, positioned almost directly between Mars and the Sun. Green. Not the pale blue-white of water ice sublimating from a comet's nucleus. Not the sodium yellow of a disintegrating asteroid. Green, the color of copper oxidizing, of certain industrial processes, of nothing that belongs in the sterile chemistry of deep space. The discovery wasn't made by Mars Reconnaissance Orbiter's science team. It was made by an amateur image processor who downloaded the raw data from NASA's public archive 3 days later. She was looking for dust devils in the Martian atmosphere. Instead, she found what she would later describe on an astronomy forum as a thumbprint on the lens of the universe. Within hours, the image circulated through the tight-knit community of planetary imaging enthusiasts. Within a day, professional astronomers began requesting observing time on ground-based telescopes. Within 2 days, the European Space Agency's Mars Express orbiter was repositioned to capture follow-up imagery. And within 3 days, the object, or objects, because no one could, yet agree on whether they were seeing one thing or many, had begun moving in a way that comets simply do not move. The initial brightness measurements suggested something between magnitude 18 and 19, far too faint for naked eye observation from Earth, but well within the detection threshold of Mars orbiting instruments. But brightness alone tells you almost nothing. A grain of sand close to your eye blocks the same amount of light as a mountain on the horizon. Distance, size, and reflectivity form an equation with too many variables. What mattered more was the spectrum. When sunlight reflects off an object, it carries with it a chemical signature, a barcode written in wavelengths. Water absorbs certain colors, carbon dioxide absorbs others. Silicate rock, metallic iron, organic compounds, each leaves its fingerprint in the reflected light. The spectrum of this object made no sense. The green emission appeared concentrated in a narrow band, around 500 nanometers, the wavelength associated, with certain metallic transitions, copper perhaps, or nickel in an excited state. But excited by what? Solar radiation at this distance, nearly 200 million kilometers from the Sun, should produce nothing like this. And there was something else in the data, something the amateur observer hadn't noticed in the visible light image. A faint secondary signal at 21 centimeters. 21 centimeters, the hydrogen line, the most fundamental frequency in radio astronomy. The same wavelength that neutral. Hydrogen atoms emit throughout the universe. The same wavelength that forms the background hum of interstellar space, and the same wavelength detected in 1977 by the Big Ear radio telescope in Ohio, in a signal so strong, so clearly artificial in its narrowband precision, that the astronomer on duty wrote "wow" in the margin of the printout. The wow signal. 72 seconds of coherent transmission from the constellation Sagittarius. Never repeated, never explained, never forgotten. Tonight, 48 years later, Mars was detecting something green and something broadcasting at 21 centimeters, and no one wanted to be the first to say out loud what several dozen astronomers were already thinking in silence. What if silence itself is the answer? The official designation came through the Minor Planet Center on October 4th, 3I Atlas. The 3I marked it as the third confirmed interstellar object ever detected, after Oumuamua in 2017 and Comet Borisov in 2019. The Atlas referred to the Asteroid Terrestrial Impact Last Alert System in Hawaii, which had captured pre-discovery images dating back to late September, though no one had noticed the object at the time. Pre-discovery images. The phrase sounds innocuous, but it carries weight. It means the object had been visible for days or weeks before anyone realized it was there. It means our sky surveys, comprehensive as they are, still miss things. It means the universe can slip past our notice, silent and patient, until the moment it chooses, or happens to reveal itself. The preliminary orbit calculation suggested an entry velocity of approximately 60 kilometers per second relative to the Sun. Fast, but not impossibly so. Oumuamua had entered at 26 kilometers per second, Borisov at roughly 32. Interstellar objects move quickly because they are not bound by the Sun's gravity. They are visitors, not residents, passing through our solar system on trajectories shaped by the gravity of stars we cannot see. But velocity is only one component of a trajectory. Direction matters more. The object was approaching from the direction of Sagittarius, the same region of sky from which the WOW signal had originated. It was traveling almost directly toward the inner solar system, on a path that would bring it within 0.3 astronomical units of Earth, closer than the orbit of Mercury, in late December 2025. And it was decelerating, not much, perhaps 0.5% over the 2-week observation window, well within the margin of error for preliminary measurements. Comets decelerate when they outgas, when solar heating vaporizes ices on their surface, producing jets of gas that act like tiny rocket engines, slowing the nucleus. This is normal, this is expected. But comets don't emit green light, and comets don't broadcast at 21 centimeters. By October 6th, 16 different observatories had confirmed detection. Hubble Space Telescope dedicated 4 orbits to imaging and spectroscopy. The James Webb Space Telescope's NIRSPEC instrument captured near-infrared data, revealing thermal signatures inconsistent with a typical comet. Ground-based facilities in Chile, Hawaii, and the Canary Islands tracked the object continuously, building up light curves and spectral time series. And then quietly the data releases stopped. NASA's public archive updated normally through October 7th, then went silent. ESA's Mars Express data portal showed scheduled maintenance. Hubble's observation logs listed the target as calibration field. JWST's public data release schedule, typically updated weekly, showed no new entries. The silence felt deliberate. Amateur astronomers continued tracking the object using backyard telescopes and makeshift radio receivers. Online forums filled with speculation, theories, calculations, but the professional community, the institutions with billion-dollar instruments and decades of expertise, said nothing. In the absence of official data, the questions multiplied. Was the object fragmenting? Were there multiple components? Was the green emission continuous or pulsed? Was the 21-centimeter signal actually coming from the object, or was it foreground contamination from Earth's ionosphere? And beneath all the technical questions lay one that no one wanted to ask directly, because asking it opened a door that might not close. If this object is artificial, if it was sent here deliberately, if it has been traveling for thousands of years across the interstellar void, why is it arriving now? Trajectories don't lie. They are the most honest language in astronomy, pure geometry written in gravity and velocity. When an object enters the solar system from interstellar space, its path is determined by 2 things: its velocity vector when it crosses the heliopause, and the gravitational influence of the Sun and planets as it falls inward. The math is old, Newtonian mechanics, solved with pencil and paper in the 18th century. The only complexity comes from perturbations, the tiny gravitational tugs from Jupiter, Saturn, and the other gas giants. But fundamentally, an interstellar trajectory is a hyperbola, an open curve that enters the solar system, swoops around the Sun, and departs back into the void. One visit, no return. The object arrives from infinity and returns to infinity, never to be seen again, unless it slows down. The orbital elements for 3I Atlas, calculated from 2 weeks of position measurements, showed something peculiar. The eccentricity, the measure of how elongated the orbit is, was hovering near 1.04. Anything above 1.0 indicates an unbound orbit, a hyperbola. Anything below 1.0 indicates an ellipse, a closed orbit, that will eventually bring the object back. At 1.04, the object should depart the solar system permanently, but that value had been dropping. On October 3rd, the calculated eccentricity was 1.06. By October 8th, it was 1.03. By October 10th, preliminary measurements suggested 1.01. Measurement uncertainty, possibly. Orbital. Elements calculated from short observation arcs are notoriously unstable. A few millimeters per second of error in velocity, compounded over millions of kilometers, can shift the calculated eccentricity significantly. But there was a pattern in the residuals, the difference between where the object was predicted to be and where it actually appeared. The residuals weren't random noise, they showed a systematic bias. The object was consistently ahead of where it should be if it were coasting on a purely gravitational trajectory. It was accelerating toward the inner solar system. Dr. Avi Loeb, the Harvard astronomer who had argued in 2018 that Oumuamua might be an artificial light sail, published a brief commentary on his blog on October 11th. He didn't speculate about intent or origin, he simply presented the numbers. If the deceleration pattern continued, the object would achieve an eccentricity below 1.0 by mid-November, placing it on a bound orbit that would make it a permanent, if highly eccentric, member of the solar system. An interstellar object that decides to stay, he wrote, raises questions that orbital mechanics alone cannot answer. The commentary was picked up by Scientific American, New Scientist, and a dozen astronomy blogs. Within hours, it had been shared 50,000 times. Within a day, the Minor Planet Center issued a terse statement emphasizing that orbital elements were still preliminary and that significant uncertainties remain in all calculated parameters. The statement didn't address the green emission. It didn't address the 21-centimeter signal. It didn't address why NASA and ESA had stopped releasing data. Silence in science is usually institutional caution, but sometimes it's something else. From a purely statistical perspective, the arrival of 3I Atlas strained probability. The solar system occupies a tiny fraction of the Milky Way's volume, less than 1/trillionth of 1%. The odds of an interstellar object passing through our neighborhood are already vanishingly small. The odds of one arriving on a trajectory that brings it close to Earth are smaller still. Now add timing. Humanity has possessed radio telescopes capable of detecting interstellar signals for approximately 70 years. We've had space-based infrared observatories capable of characterizing distant objects for about 30. The window in which we could detect and study something like 3I Atlas represents roughly 0.001% of Earth's geological history. And yet here it is, arriving precisely during that narrow window, from the same direction as the only unexplained radio signal we've ever detected, on a trajectory that brings it closer to Earth than any confirmed interstellar object in recorded history. Coincidence is always possible. The universe is large, and large systems produce rare events simply through repetition. Flip a coin 1 billion times and you'll eventually get 20 heads in a row. But you'll also notice when it happens. We were noticing. The amateur astronomy community, denied fresh data from official sources, turned to archival research. If 3I Atlas had been captured in pre-discovery images by Atlas in Hawaii, perhaps other surveys had seen it too. Pan-STARRS, the Catalina Sky Survey, the Zwicky Transient Facility, all conduct nightly sweeps of the sky, archiving terabytes of data. Within 3 days, volunteers had found it in 6 different archival datasets, extending the observation baseline back to August 15, 2025. With nearly 2 months of positional data, the orbital elements became far more precise. The eccentricity was definitely dropping, and the trajectory, when extrapolated backward in time, pointed to a very specific origin. Not just Sagittarius, not just the general direction of the galactic center, but a region of sky within 2 degrees of the coordinates where the WOW signal had been detected in 1977. 2 degrees is not precise by astronomical standards. It represents an area of sky containing thousands of stars. But it's not nothing. And when you factor in the proper motion of stars over 48 years, the uncertainty cone narrows. There were 11 stars within the calculated origin region that would have been aligned with the WOW signal coordinates in 1977. None were particularly remarkable. G-type and K-type main sequence stars, yellow and orange, similar in temperature and size to the Sun. The nearest was 122 light-years away, the farthest 187. If 3I Atlas had been launched from one of those systems in 1977, traveling at 60 kilometers per second, it would have taken roughly 600 to 900 years to reach us, which meant it couldn't have been launched in response to the WOW signal. It would have had to be launched centuries earlier, long before humans invented radio, long before we announced our presence to the cosmos, unless the WOW signal wasn't a greeting, unless it was a notification, a beacon, perhaps, transmitted automatically when a probe reached a certain milestone. A signal sent not to Earth but back to its origin saying arrived. The hypothesis was neat. Too neat. Science doesn't reward neatness. It rewards testable predictions. And this hypothesis made one very clear prediction. If 3I Atlas was artificial, if it had been traveling for centuries, if it had sent a signal home in 1977 upon entering the outer solar system, then it might send another signal when it reached the inner system, in late December, when it passed within 0.3 astronomical units of Earth, when every radio telescope on the planet would be listening. The data waits, and so do we. Comets are fragile. This is one of the fundamental truths of planetary science. They are not solid rocks, but loose aggregates, rubble piles of ice and dust, held together by their own feeble gravity and the frozen adhesion of water molecules. When a comet approaches the Sun, thermal stress fractures the nucleus. Gas pressure builds in subsurface voids. Eventually, the structure fails. The comet splits, sometimes into 2 or 3 large fragments, sometimes into dozens of smaller pieces that spread along the orbit like beads on a string. Comet Shoemaker-Levy 9 famously fragmented into 21 pieces before colliding with Jupiter in 1994. Comet Linear disintegrated entirely in 2000, dissolving into a cloud of dust. Fragmentation is common. It's expected. It's one of the ways comets die. But comets fragment forward, in the direction of travel. Physics demands it. When internal pressure ruptures the nucleus, the released gas pushes fragments apart along the comet's trajectory. The pieces spread out over time, leading and trailing the main body, but always maintaining the same general direction of motion. 3I Atlas was fragmenting backward. The anomaly first appeared in images from the ESA's Trace Gas Orbiter on October 9th, during a brief window when the spacecraft's Cassis camera was pointed toward the object's calculated position. The primary detection remained consistent with earlier observations, a diffuse green glow approximately 200 kilometers in apparent diameter, though the actual size remained uncertain without knowing the object's distance precisely. But behind it, along the trajectory it had already traveled, were 3 additional glows, fainter, smaller, spaced at irregular intervals stretching back across several 100,000 kilometers. They hadn't been there in the October 2nd images. The initial interpretation was straightforward. The object had fragmented sometime between October 2nd and October 9th, and the fragments were drifting apart. Except fragments should drift forward, carried by the momentum of outgassing. These were drifting backward, as if they had been left behind deliberately, or as if they had been released. The spectroscopic data from JWST's NIR-SPEC instrument, quietly released to a handful of researchers under strict embargo, showed something equally strange. The ET trailing objects had different spectra than the primary target. The main object showed that peculiar green emission at 500 nanometers, along with weak absorption features consistent with carbon dioxide ice. The trailing objects showed almost no green emission, but strong absorption bands in the near-infrared consistent with organic compounds, complex hydrocarbons perhaps, or even prebiotic molecules. Different chemistry, different thermal properties, different reflectivity. It was as if the main object was shedding pieces of itself that bore no chemical relationship to the parent body, like a ship jettisoning cargo containers. Amateur observers, tracking the system with backyard radio receivers, reported that the 21-centimeter emission was also changing. The signal wasn't constant. It pulsed with a period of approximately 47 seconds, and the pulses were getting stronger as the object approached the Sun. 47 seconds. Not a round number by human standards, but round numbers. Are cultural artifacts. There's no reason to expect an extraterrestrial signal to pulse every 30 seconds or every minute. But 47 seconds is long enough to encode information, long enough to transmit a message if you know the language. The Big Ear telescope in 1977 had detected the WOW signal for 72 seconds, the maximum duration possible given the telescope's fixed position and the Earth's rotation. The signal had drifted through the receiver's beam as the planet turned, rising in intensity, peaking, then fading. Total duration, 72 seconds. 72 is not a multiple of 47. But if you assume the 1977 signal was also pulsed and you catch it mid-cycle, the observed duration depends entirely on when you started listening. Start listening 3 seconds before a pulse, and you might record 72 seconds total before the signal leaves the beam. Miss the pulse entirely, and you record silence. The WOW signal was detected exactly once, despite follow-up observations, which means either it was never repeated or it was repeated but we weren't listening at the right time. If 3i Atlas was pulsing every 47 seconds, and if the 1977 WOW signal had the same period, then the chance of Big Ear catching even a single pulse during its brief observing window was less than 2%. We got lucky once. We might not get lucky again. By October 12th, the object's brightness had increased to magnitude 16, making it accessible to amateur astronomers with moderately sized telescopes. Observers across the Northern Hemisphere began posting images to online forums, each showing the same configuration: 1 bright central glow, 3 fainter trailing glows, all green, all moving together across the star field. Except when you compared images taken hours apart, something else became apparent. The trailing objects weren't just drifting backward, they were decelerating faster than the main body. The spacing between them was increasing, not linearly but exponentially. At the current rate, they would fall so far behind that they'd be undetectable within 2 weeks, unless they changed course. On October 14th, an observer in New Mexico captured a time-lapse sequence spanning 6 hours. In the final frame, one of the trailing objects had vanished. Not faded, vanished. It was there at 02:30 UTC. It was gone at 02:45 UTC. 15 minutes. Objects in space don't disappear in 15 minutes. Even if a comet fragment completely sublimated, vaporized into gas, the resulting debris cloud would remain visible for hours, scattering sunlight as it expanded. This was different. It was as if someone had switched off a light. The observer posted the sequence with a simple caption: "Can someone check my calibration? I think I'm losing my mind." 14 other observers confirmed it. Same time, same coordinates, same disappearance. The second trailing object vanished on October 16th. The third on October 18th. By October 20th, only the primary object remained, and it was brighter than ever. Spectroscopy is detective work. You take light, split it into component wavelengths, and read the chemical signature left behind. Every element, every molecule, every atomic transition produces a unique pattern. Absorption lines where certain wavelengths are missing, emission lines where others are enhanced. Hydrogen absorbs at 656 nanometers, oxygen at 630, sodium at 589. These lines are as reliable as fingerprints, unchanged. Across billions of light years, when we analyze the light from a distant galaxy, we see the same hydrogen lines, just shifted in wavelength by the expansion of space. The physics is universal, which is why the spectrum of 3i Atlas was so profoundly unsettling. The green emission at 500 nanometers didn't match any common cometary molecule. It wasn't hydroxyl radical, which produces green emission around 508 nanometers in some comets. It wasn't diatomic carbon, which emits in the green around 516 nanometers. It wasn't oxygen, nitrogen, or any of the expected volatiles. The closest match was neutral nickel, atomic nickel in an excited state, emitting photons as electrons dropped from higher to lower energy levels. Nickel emission at 500 nanometers requires ultraviolet excitation, typically from a hot star or an active energy source. The sun's ultraviolet output at Mars's distance is far too weak to produce this effect in any significant quantity. And there was another problem. Nickel doesn't exist in isolation in comets. It's bonded to iron in metallic grains, the remnants of ancient supernovae mixed into the primordial cloud from which the solar system formed. When comets outgaze, they release dust, tiny particles of rock and metal, but not free atoms of nickel. The vaporization temperature is too high. Nickel sublimes at 3000 Kelvin, far hotter than any comet's surface, unless the nickel wasn't coming from ice, unless it was coming from something metallic being ablated, eroded, heated not by sunlight, but by some internal process. The spectrum also showed something else, something that made no chemical sense at all. There were emission lines in the ultraviolet, consistent with ionized magnesium and ionized calcium. These are common in comets, produced when solar ultraviolet light strips electrons from metal atoms in the coma. But the intensity ratios were wrong. In natural comets, magnesium and calcium appear in roughly equal proportions, reflecting their cosmic abundance. In 3I Atlas, the calcium emission was 8 times stronger than magnesium. 8 times. Calcium is more abundant than magnesium in Earth's crust by about a factor of 2, but in cosmic dust, in primitive solar system material, the ratio is near unity. Seeing an 8-fold enrichment suggested fractionation, some process that had selectively concentrated calcium while depleting magnesium. Biological processes do this. Bones and shells concentrate calcium. So do certain bacteria that precipitate calcium carbonate in sedimentary environments. But so do industrial refining processes. If you were building something from raw asteroid material and you needed calcium for structural components or chemical feedstock, you might extract it preferentially, leaving magnesium behind in the slag. This is speculation. It has to be. But speculation built on data is different from speculation built on imagination. The data said, nickel emission without iron, calcium enrichment without geological context, green glow without molecular origin. The data said this doesn't fit, and when data doesn't fit, you have 3 options. You can assume you're measuring wrong, you can assume the theory is wrong, or you can assume the object is unlike anything you've seen before. The first option, measurement error, was quickly ruled out. 6 different instruments on 4 different spacecraft had captured consistent spectra. Hubble's STIS spectrograph, JWST's NIR spec, ESA's UVEs on the Very Large Telescope in Chile, and Mars Express's SPICAM all showed the same anomalous emission lines. The second option, bad theory, was harder to dismiss, but equally unlikely. Atomic spectroscopy is among the most well-tested branches of physics. We've been doing it for over a century. The quantum mechanics of electron transitions is not under debate. Which left the third option. The object was unlike anything we'd seen before, but unlike anything spans a vast conceptual space. A comet from a different stellar system might have unusual chemistry, shaped by different formation conditions, different isotopic ratios, different parent cloud composition. That would be remarkable, Nobel Prize remarkable, but still natural. An object shedding fragments backward while emitting metallic vapors and pulsing radio signals at the hydrogen line is not just unusual. It strains the framework of natural processes so severely that the framework begins to crack. And yet, we hesitate. We hesitate because the leap from doesn't fit to artificial is enormous. It requires discarding every natural explanation, no matter how improbable, before considering the extraordinary. It requires accepting that we are not alone, that we have never been alone, and that something built by minds we cannot imagine is passing through our solar system at this exact moment in history. We hesitate because extraordinary claims demand extraordinary evidence. But what evidence would suffice? A radio signal broadcasting, "Hello, Earth?" The object isn't doing that. It's pulsing at 21 centimeters, the hydrogen line, yes, but also a natural frequency emitted by hydrogen throughout the universe. It could be natural interference, it could be coincidence. The green nickel glow, unusual but not impossible, Perhaps there's a thermal process we don't understand. Perhaps ultraviolet fluorescence is more efficient than models predict. The backward fragmentation? Strange, but comet physics is complex. Perhaps gas jets are isometric. Perhaps rotational dynamics are involved. Every anomaly taken individually has a possible natural explanation. Improbable, yes, stretching the bounds of known physics, certainly. But possible. It's only when you combine them, when you step back and see the full picture, that the natural explanations begin to collapse under their own collective improbability. And even then, we hesitate. Because once you say it, once you entertain the hypothesis openly, the burden of proof becomes crushing. You're no longer proposing a new comet model. You're proposing that humanity's existential assumptions are wrong. So we wait. We gather more data. We refine the measurements. We search for the natural explanation that makes everything fit. And while we wait, 3i Atlas continues inward, growing brighter, pulsing faster, shedding pieces of itself like breadcrumbs across the void. Would we even recognize intelligence if it weren't trying to speak? Comet tails point away from the sun. This is not a tendency. It's a law. Solar radiation pressure pushes dust particles outward, creating a curved dust tail that follows the comet's orbital path. The solar wind, a stream of charged particles flowing from the sun, pushes ionized gas even more efficiently, creating a straight ion tail that points radially away from the sun, regardless of the comet's direction of travel. Two tails, both pointing away from the sun. Always, except when they don't. The phenomenon is called an anti-tail, and it's one of the strangest optical effects in cometary science. It appears as a spike of light pointing toward the sun, directly contradicting the fundamental physics of radiation pressure. It looks impossible, like watching smoke blow into a fire. The explanation when it comes is geometrical. The anti-tail isn't actually pointing sunward. It's a tail of heavy dust particles lying in the comet's orbital plane, seen edge-on from Earth. When the geometry aligns just right, when Earth crosses the comet's orbital plane, we see the dust tail projected toward us, appearing to point toward the sun. It's an illusion, a perspective effect. Anti-tails are rare, but not unheard of. Comet Arendt-Roland in 1957 displayed one. So did Comet Hale-Bopp in 1997, though only briefly. They last a few days at most, visible only when the viewing geometry is perfect. 3i Atlas had been displaying an anti-tail for 2 weeks. The first clear image came from Hubble on October 21st. The observation was part of a multi-wavelength campaign involving simultaneous imaging in ultraviolet, visible and near-infrared. The visible light image showed the now familiar green coma, the diffuse cloud of gas and dust surrounding the nucleus, approximately 400 kilometers in diameter, and extending from it back toward the sun, a narrow spike of brightness stretching over 2,000 kilometers. If this were a perspective effect, it should have vanished within days as Earth's motion changed the viewing angle. But follow-up. Observations on October 23rd, 25th and 27th showed the anti-tail persisting, unchanged in length and orientation. The geometry wasn't aligning. Earth had moved substantially in its orbit. Mars had moved. The sun itself had rotated. Yet the anti-tail remained, pointing back along the trajectory the object had traveled, as if marking the path it had taken, or illuminating the breadcrumb trail it had left behind. The spectroscopic analysis of the anti-tail made things worse. Normal anti-tails are composed of heavy dust particles, silicate grains, micron-sized rocks, reflecting sunlight. The spectrum should be featureless, a smooth continuum matching the sun's output with slight reddening from scattering. The anti-tail of 3i Atlas showed emission lines. Specifically, it showed emission at 500 nanometers, the same nickel emission seen in the coma, but also emissions at 589 nanometers, sodium, 630 nanometers, oxygen, and a forest of faint lines in the blue and ultraviolet consistent with ionized metals. Dust doesn't emit light, it reflects light. Emission requires energy, either thermal energy hot enough to excite atoms or energetic radiation strong enough to ionize gas. The anti-tail was glowing from within. Thermal emission was ruled out immediately. The calculated temperature, based on distance from the Sun, should be around 200 Kelvin, well below the threshold for visible emission. To glow at 500 nanometers from thermal radiation alone, the material would need to be heated to 6,000 Kelvin, hotter than the surface of the Sun, which left external excitation. Something was energizing the material in the anti-tail, exciting electrons to higher energy states, causing them to emit photons as they relaxed back down. Solar ultraviolet could do this in principle, but the intensity required to produce the observed brightness would need to be far stronger than what the Sun provides at this distance. You'd need a nearby source of ultraviolet light, a young hot star or an object emitting its own ultraviolet radiation. The hypothesis was almost too direct. If the anti-tail was being illuminated by ultraviolet light from the nucleus of 3I Atlas itself, then the nucleus wasn't just reflecting sunlight, it was generating light. Power generation, internal energy, not solar panels, not thermocouples passively harvesting heat, but active energy production at a level sufficient to emit detectable ultraviolet across thousands of kilometers of space. That's not a comet, that's a machine. The dynamics of the anti-tail posed another problem. If the material was being left behind along the trajectory, shed from the object as it traveled, then it should be spreading out, diffusing, dissipating over time. Dust particles released into space don't maintain formation. They drift, each on its own subtly different trajectory, until the trail becomes so dispersed, it's no longer detectable. The anti-tail of 3I Atlas wasn't spreading. If anything, it was becoming more defined. By October 28th, high-resolution imaging from JWST showed structure within the anti-tail, faint clumps and nodes spaced at irregular intervals, as if the material was organizing itself, or being organized. Electromagnetic forces can organize dust under the right conditions. Charged particles respond to magnetic fields, aligning along field lines, creating structure. This happens in planetary rings, where Saturn's spokes are thought to form from electrically charged dust levitated above, the ring plane. But planetary rings are embedded in strong magnetic fields generated by the planet's dynamo. Interstellar space has no such field. The Sun's magnetic field at this distance is negligible, too weak to organize dust on the scales being observed, unless the object was generating its own magnetic field. Spacecraft generate magnetic fields to protect electronics from radiation. Earth generates one from the churning motion of molten iron in its core. Magnetars, neutron stars with extreme magnetic fields, generate one strong enough to warp atomic structure from light years away. 3I Atlas was not a neutron star, but if it was artificial, if it had been traveling through interstellar space for centuries, it would need shielding against cosmic rays, high-energy particles that degrade materials and scramble electronics over time. A magnetic field would do that. Not a planet-strength field, but something localized, controllable, projected outward like an umbrella. And if you were leaving behind a trail either as navigation markers or deployed instruments, you might use magnetic anchoring to keep them in formation. Small devices, each with its own power source, each responding to magnetic control signals from the primary object, each glowing green as metal atoms ablate from their surfaces under ultraviolet excitation. This is speculation layered on speculation, inference built on inference. But it's constrained speculation. The data says persistent anti-tail, emission, spectrum, organized structure, energy source. The physics says not thermal, not solar, not natural dust dynamics. The gap between what the data shows and what natural processes can explain is widening, and as it widens, the alternative becomes harder to ignore. Chemistry in space is different from chemistry on Earth. It's slower, colder, governed by reactions that would never occur in a terrestrial laboratory. Molecules form on the surfaces of dust grains over millions of years. Ices accumulate in the shadows of molecular clouds. Organic compounds, the building blocks of life, assemble through processes we still don't fully understand. But the rules are universal. Carbon bonds to oxygen, hydrogen, nitrogen. Silicon bonds to oxygen, forming silicates, rock. Metals exist as grains, tiny fragments of stellar debris locked into larger particles. You don't find pure nickel floating free in space. You don't find calcium without magnesium. You don't find emission spectra that defy every known chemistry, unless someone assembled them that way. The full spectroscopic dataset from VLT's UV-ESE spectrograph was quietly uploaded to a secure server on October 30th and shared with a select group of researchers under embargo. The data covered wavelengths from 300 to 1,000 nanometers, ultraviolet through visible into near-infrared, with spectral resolution high enough to distinguish individual atomic transitions separated by fractions of a nanometer. What they found didn't just violate expectations. It violated the known chemistry of solar system formation. The most prominent feature remained the nickel emission at 500 nanometers, but now with enough resolution to see fine structure, multiple closely spaced lines indicating nickel atoms in different energy states. The intensity distribution suggested temperatures around 4,000 Kelvin for the emitting region. 4,000 Kelvin. Hot enough to melt iron. Hot enough to vaporize most ices instantly. Yet the spectrum also showed strong absorption features from carbon dioxide ice at 4.3 microns, indicating surface temperatures no higher than 200 Kelvin. The object was simultaneously frozen and molten. The only way to reconcile this was compartmentalization. The bulk of the object remained cold, covered in carbon dioxide frost. But somewhere, perhaps in localized regions, perhaps in internal chambers, something was generating intense heat, hot enough to vaporize metallic elements. This happens naturally in one context: asteroid impacts. When a high-velocity projectile strikes rock, the kinetic energy converts to heat in microseconds, creating temperatures high enough to melt stone and vaporize metal. Impact plumes can reach 10,000 Kelvin or higher, but impacts are transient. They last seconds. The thermal signature decays rapidly as the vaporized material expands and cools. 3I Atlas had been emitting nickel vapor continuously for at least 4 weeks. That required sustained energy input, not a single collision. The calcium to magnesium ratio remained inexplicably high, 8.1 in the most recent measurements. But now there was additional context. The spectrum also showed emissions from aluminum, 396 nanometers, titanium, 498 nanometers, and trace amounts of chromium, 425 nanometers. These are structural metals: aluminum for lightweight strength, titanium for heat resistance, chromium for corrosion protection. In cosmic abundances, they're rare, parts per million in primitive solar system. Material. In spacecraft alloys, they're essential. The pattern was becoming harder to dismiss. You could find each element individually in natural contexts. Aluminum in clay minerals, titanium in refractory grains that condensed near young stars, chromium in metallic meteorites. But finding them together in ratios inconsistent with cosmic abundances, in an object emitting heat and radio signals and shedding organized debris, the natural explanations were collapsing. There was one more: spectroscopic anomaly, buried in the ultraviolet data, that took days to notice because no one was looking for it. At 656 nanometers, the hydrogen alpha line, there should have been strong emission. Hydrogen is the most abundant element in the universe. Comets are partially composed of water ice. When solar ultraviolet breaks apart water molecules, it releases hydrogen atoms that emit at 656 nanometers. Every comet shows this line. It's one of the defining spectroscopic signatures of cometary activity. 3I Atlas showed almost no hydrogen alpha emission. The weakness was striking. Based on the carbon dioxide emission and the estimated size of the coma, the hydrogen alpha line should have been easily detectable, one of the brightest features in the spectrum. Instead, it was barely above the noise level, 90% weaker than expected, which meant either the object contained almost no water or the water was being consumed before it could dissociate into hydrogen. The CO2-H2O ratio, estimated from infrared absorption features, was already unusual. 8:1, far higher than typical comets, which show ratios closer to 1.1 or 2.1. Comets are dirty snowballs, mixtures of water ice and carbon dioxide ice in roughly equal proportions. An 8:1 ratio suggested either preferential water loss over the object's history or formation in an extremely cold, carbon-rich environment. But even with an 8.1 ratio, there should still be enough water to produce detectable hydrogen emission. The E absence was puzzling, unless the water wasn't being released as vapor, unless it was being used. Electrolysis, splitting water into hydrogen and oxygen using electrical current, has been understood since the 18th century. It's the basis of fuel cells, life support systems, and propellant production. You pass electricity through water, and you get hydrogen gas and oxygen gas. If you then burn the hydrogen, combine it with oxygen in a controlled reaction, you get energy and water vapor. But if you separate the products, storing the hydrogen in one container and the oxygen in another, you've created a battery, a chemical energy storage system. Spacecraft do this. The space shuttle did this. Modern fuel cells do this. You produce hydrogen and oxygen when you have excess power, say from solar panels in bright sunlight, and recombine them when you need power, like during eclipse or high-demand operations. If 3I Atlas was consuming water through electrolysis, it would release carbon dioxide, which can't be easily broken down without extreme energy input, while sequestering hydrogen. The spectral signature would show exactly what observers were seeing: strong CO2 emission, weak hydrogen emission, and evidence of oxygen in the form of ionized oxygen lines at 630 nanometers. The oxygen emission was there, faint but present. Ionized oxygen at 630 nanometers, requiring ultraviolet excitation or electrical discharge to produce. The pieces fit too well. Carbon dioxide venting naturally, water being electrolyzed, oxygen ionized by electrical activity, hydrogen stored or consumed internally, metals vaporized by waste heat. This wasn't a comet outgassing passively under solar heating. This was a system managing resources, converting one form of energy to another, generating heat as a byproduct and maintaining operations over weeks of continuous observation. The data waits, and so do we. But the data was no longer ambiguous. Science operates on frameworks, paradigms built from decades of accumulated evidence, refined through generations of observation and theory. These frameworks are robust because they explain vast numbers of phenomena with minimal assumptions. Gravity explains planetary orbits, falling apples, and the structure of galaxies. Evolution explains the diversity of life, the fossil record, and antibiotic resistance. Frameworks are tested constantly, and they survive because they work. But occasionally, data appears that doesn't fit. Not marginally, not within error bars, but fundamentally. And when that happens, you have a choice: expand the framework or replace it. The framework for understanding comets is old and well-tested. Dirty snowballs from the outer solar system, occasionally perturbed into orbits that bring them near the sun, where heating causes sublimation and outgassing. The chemistry follows from formation conditions in the protoplanetary disk. The dynamics follow from Newtonian mechanics and thermodynamics. Comets are predictable. 3I Atlas wasn't predictable. By November 1st, the object had brightened to magnitude 14.5, making it accessible to amateur astronomers with modest equipment. Dozens of observers were tracking it nightly, posting images and spectra to online forums. The professional observatories remained largely silent. Data was being collected, but little was being released publicly. The silence fueled speculation. In the absence of official explanations, the amateur community began constructing its own. The most popular theory circulating through forums and comment threads was the precursor hypothesis. The idea was simple. 3I Atlas wasn't a comet. It was a probe, an autonomous spacecraft sent by an extraterrestrial civilization to survey the solar system. Not recently sent, but centuries or millennia ago. Perhaps even millions of years ago, long before humanity existed. The probe would have entered the outer solar system, moving slowly to avoid detection, surveying the planets from a distance. It would have transmitted its findings home, not as a continuous stream, but as periodic bursts, timed to moments when the signal would be least ambiguous, perhaps when passing through certain regions of space, perhaps when reaching certain milestones in its mission. In 1977, the probe might have transmitted such a signal, a brief pulse at 21 centimeters, the universal marker of hydrogen saying, "Arrived, beginning inner system survey." We detected it for 72 seconds. We called it the wow signal. We searched for repetition and found nothing because it wasn't meant to repeat. It was a one-time notification, a message sent home across light years, acknowledging mission progress. Now, 48 years later, the probe was completing its survey, approaching the inner planets for close observation. It was decelerating, adjusting its trajectory, shedding components no longer needed. It was preparing for the final phase of its mission. And it was emitting signals, not to communicate with us, but as part of its operational protocols. Telemetry status updates, course corrections broadcast at 21 centimeters because that frequency propagates efficiently through interstellar space. We were watching a machine do its job, oblivious to our presence, following instructions written before humans discovered fire. The hypothesis explained everything: the trajectory from Sagittarius, the timing, the wow signal, the anomalous chemistry, the energy emissions, the organized anti-tail, the 47-second pulse period. It explained everything except one thing. If the probe wasn't here to communicate, why was it approaching Earth so closely? Survey missions observe from a distance. You don't need to pass within 0.3 AU of a planet to study it. Mars-orbiting spacecraft can image Earth in exquisite detail from 100 million kilometers away. Jupiter's moons have been mapped from orbit without landing. There's no scientific reason for a probe to approach Earth this closely, unless Earth is the target. Not for communication, not for contact, but for detailed observation, high-resolution imaging, spectroscopy of the atmosphere, maybe even sampling, scooping up particles from the upper atmosphere, analyzing isotopic ratios, searching for biosignatures. If an extraterrestrial civilization wanted to know whether Earth harbored life, this is how they'd do it. Send a probe, wait for it to arrive, have it make a close pass, gathering data too detailed to obtain from light years away, and then have it transmit home. The precursor hypothesis wasn't fringe speculation confined to conspiracy forums. By early November, it was being discussed openly in academic preprints and opinion pieces. A paper posted to Archive on November 3rd, authored by researchers at the SETI Institute, laid out the argument methodically: the probability of natural explanations, the cumulative improbability of multiple anomalies, the alignment with the wow signal, the chemical signatures inconsistent with cometary material. The paper stopped short of declaring 3I Atlas artificial, but it concluded with a single carefully worded sentence: the hypothesis that 3I Atlas represents technology of non-terrestrial origin cannot be excluded based on available data. Cannot be excluded. In scientific language, that's as close to an endorsement as you get without definitive proof. It's an acknowledgement that the natural explanations have failed, that the data is pointing towards something extraordinary, and that the community needs to prepare for the possibility that we are observing something built by minds not our own. The paper was downloaded 40,000 times in the first 24 hours. It was cited in Nature, Science, and the New York Times. It was debated on television, discussed in parliaments, and analyzed in classified briefings at space agencies around the world. And through it all, 3I Atlas continued inward, pulsing steadily, glowing green, trailing its organized debris field, indifferent to the chaos it had created in the minds of those watching. Institutions exist to manage uncertainty. They accumulate expertise, build consensus, establish protocols for handling complex information. When something unexpected happens, a new disease, a market crash, an astronomical anomaly, institutions are supposed to provide clarity. But sometimes institutions go silent. By mid-November, the silence from NASA, ESA, and other major space agencies had become conspicuous. Data releases had slowed to a trickle. Press conferences were cancelled or postponed. Requests for interviews with scientists involved in 3I Atlas observations were declined or redirected to public affairs offices that offered only boilerplate statements. Observations are ongoing, analysis is preliminary. We will release findings through proper scientific channels when the data has been thoroughly reviewed. The statement said nothing, and saying nothing, when the world is asking questions, is itself a form of communication. The silence wasn't universal. Individual researchers continued posting findings to preprint servers. University press offices issued statements from professors commenting on publicly available data. Amateur astronomers shared observations freely, but the large institutions, the ones with billion-dollar budgets and multi-decade missions, remained quiet. There are benign explanations for institutional silence. Data quality checks take time. Peer review takes time. Extraordinary claims require extraordinary vetting before publication. Agencies have reputations to protect and legal obligations to meet. Announcing something prematurely, only to retract it later, damages credibility. But there are other explanations. If 3I Atlas is artificial, if it represents unambiguous evidence of extraterrestrial technology, then the implications extend far beyond astronomy. Defense agencies want to know if it poses a threat. Governments want to manage public reaction. International treaties govern the handling of potential extraterrestrial contact. The 1967 Outer Space Treaty, ratified by over 100 nations, contains provisions for consultation and cooperation in the event of detecting extraterrestrial life. Consultation takes time. Cooperation requires coordination, and coordination across dozens of nations, each with different interests and perspectives, is slow. In the meantime, silence becomes policy. The amateur astronomy community, unbound by institutional constraints, filled the void. Online forums became clearinghouses for observations, speculations, and calculations. Some of the analysis was sophisticated, multi-wavelength light curves, orbital refinements based on astrometric positions, signal processing of the 21-centimeter pulses. Some of it was nonsense, claims of visible surface structures, interpretations of the pulse pattern as encoded messages, conspiracy theories about government cover-ups. The signal-to-noise ratio was low, but buried in the noise were genuine insights. One amateur radio astronomer, working with a homemade dish antenna and software-defined radio receiver, detected structure in the 21-centimeter pulses that hadn't been reported in official data releases. The pulses weren't uniform. They varied slightly in intensity and duration, following a pattern that repeated every 19 cycles. 19 pulses, one cycle, each pulse lasting 47 seconds, each cycle lasting approximately 15 minutes. 15 minutes is significant in radio astronomy. It's roughly the time it takes for a radio source to drift through the beam of a fixed antenna as Earth rotates. It's the natural timescale for observing transient signals. If the pulse pattern was designed to be detected by civilizations using radio astronomy, a 15-minute cycle makes sense. It's long enough to provide repetition, ensuring the signal isn't dismissed as noise, but short enough to be captured during a single observation session. The amateur astronomer posted his findings with meticulous documentation, equipment specifications, observation logs, signal processing methods, statistical analysis showing the pattern was well above chance. Within hours, other observers confirmed it using their own receivers. The pattern was real, and embedded in the pattern, if you looked closely enough, was something that might be structure. Not a message, nothing so direct, but variation, modulation, the kind of complexity that suggests information content, or the kind of complexity that emerges naturally from mechanical processes, rotating machinery, oscillating components, resonances in physical structures. The interpretation remained ambiguous, but the data kept accumulating. By November 15th, the object had brightened to magnitude 13, approaching the threshold of naked-eye visibility under perfect dark sky conditions. Observers at remote sites reported seeing it as a faint, Green star near the constellation Ophiuchus, drifting slowly eastward against the background stars. The psychological impact of visibility cannot be overstated. An astronomical object detectable only through telescopes remains abstract, a data point, a set of numbers, a puzzle for specialists. But something visible to the unaided eye becomes real in a visceral way. You can point at it, you can watch it move, you can see with your own biology light that left the object minutes earlier and, traveled across millions of kilometers to reach your retina. People began gathering at observatories, planetariums, and dark sky sites, asking to see the object. Some brought binoculars, some brought cameras, some simply stood outside, staring up, trying to pick out the faint green point among thousands of other stars. They wanted to see it with their own eyes, not because observation would reveal anything new. Professional instruments had captured far better data, but because seeing creates connection. It transforms an abstraction into an experience, and humans are wired to find meaning in experiences. Mass is the most fundamental property of an object and the hardest to measure remotely. You can measure brightness easily. Photons arrive. You count them. You can measure spectrum, split the light, record the wavelengths. You can measure position and velocity, track the object over time, calculate the trajectory. But mass requires gravity. You need to see how the object pulls on other things or how other things pull on it. For asteroids passing near Earth, you can sometimes detect gravitational perturbations in spacecraft trajectories. For binary stars, you can measure orbital periods and separations, then calculate masses from Kepler's laws. For an isolated object in deep space, you're limited to indirect methods. The first mass estimate for 3I Atlas came from modeling the outgassing. If you know how much gas is being released, estimated from spectroscopic brightness, and you know the escape velocity required for gas to leave the surface, you can infer the surface gravity. And from surface gravity, assuming a shape and density, you can estimate mass. The calculation suggested a mass of at least 33 billion tons. 33 billion tons sounds enormous. For comparison, the Great Pyramid of Giza has a mass of about 6 million tons. The iceberg that sank the Titanic was perhaps 500,000 tons. 33 billion tons is 5,000 times the mass of the iceberg, a mountain of ice and rock drifting through space. Except the number came with caveats. The escape velocity depends on the object's radius, which was uncertain. The brightness of emission lines depends on excitation efficiency, which was poorly constrained. Change the assumptions slightly, and the mass estimate could shift by factors of 2 or 3 in either direction. Still, even with uncertainties, the order of magnitude was clear. Billions of tons, not millions. This was not a small object. But there was a second constraint on mass, independent of outgassing models: the trajectory. When 3I Atlas made its close approach to Mars in early October, the gravitational interaction, however slight, would have perturbed both bodies. Mars, being far more massive, would barely notice. But the object's trajectory should have deflected measurably. Tracking data from October showed no detectable deflection. That placed an upper limit on how light the object could be. If it were too light, Mars' gravity would have bent its path significantly. The absence of deflection meant the object was heavy enough to resist perturbation, which, given the distance of closest approach, 29 million kilometers, and Mars's mass, implied a minimum mass similar to the outgassing estimate. The two independent methods agreed: 33 billion tons plus or minus a factor of 2. Now came the problem: volume. High-resolution imaging from JWST, processed through advanced deconvolution algorithms, resolved the nucleus, the solid core of the object, as a slightly elongated shape approximately 800 meters long and 400 meters wide. Not perfectly resolved, but sufficient to estimate volume. If you assume a prolate ellipsoid, a stretched sphere, with those dimensions, the volume is roughly 0.1 cubic kilometers. That's 100 million cubic meters. 33 billion tons in 100 million cubic meters gives an average density of 330 kilograms per cubic meter. That's impossible. Water ice has a density of 920. Kajdish M3. Carbon dioxide ice is denser, around 1,600 kcm3. Rock is denser still, around 3,000 kcm3. Even loosely packed rubble, the kind of structure suspected for cometary nuclei, has densities well above 500 kcm3. A density of 330 kcm3 is lower than styrofoam. It suggests the object is mostly empty space, a hollow shell perhaps, or a lattice structure with vast internal voids. Natural objects aren't hollow. Gravity prevents it. As objects grow larger than a few hundred meters, self-gravity compresses the interior, squeezing out voids. You can't have a kilometer-sized object with the density of foam and expect it to remain structurally intact over millions of years, unless it's held together by something other than gravity, unless there's internal structure, walls, supports, pressurized compartments, unless it's built. The mass problem didn't resolve itself with better data. Follow-up observations through November refined the size estimate slightly, but the density remained inexplicably low. Researchers proposed alternatives. Maybe the outgassing models were wrong, overestimating mass by a factor of 10. Maybe the size estimates were wrong, underestimating volume by the same factor. Maybe both errors coincidentally balanced. But the trajectory data was hard to dispute. The lack of deflection near Mars placed firm constraints on mass, and the JWST images, while not perfect, were the highest resolution ever obtained of an interstellar object. The size estimate might be off by 20%, maybe 30%, but not by a factor of 10. Which left one uncomfortable conclusion. The object had structure, internal cavities, compartmentalization. The kind of engineering you'd use if you were building something designed to travel through space for centuries, carrying instruments and systems and perhaps even stored resources. A fuel tank would be hollow, so would a habitation module, so would a cargo bay. This is speculation, but it's constrained by numbers. The data says low. Density, high mass, solid nucleus. The physics says not possible naturally. The gap between the two is filled by inference, and the inference points toward design. By late November, the object's trajectory had been refined to high precision. Dozens of astrometric positions spanning nearly 3 months allowed orbital elements to be calculated with confidence. Perihelion, the point of closest approach to the Sun, would occur on December 22, 2025, at a distance of 0.85 astronomical units. That's well outside Earth's orbit, safely beyond any collision risk, but close enough for the object to experience significant solar heating. More significantly, the trajectory would bring it within 0.29 AU of Earth on December 18th. 29 hundredths of an astronomical unit, approximately 43 million kilometers, closer than any confirmed interstellar object in recorded history, closer than Mars at its nearest approach, close enough that ground-based telescopes would resolve surface features, if any existed, close enough that radar observations might be feasible, close enough to matter. The approach geometry was also remarkable. The object wasn't passing through the ecliptic plane at a steep angle, as most interstellar objects do. Its trajectory lay almost within the plane, tilted only 8 degrees from the orbital paths of the planets. That's unusual. Interstellar objects enter the solar system from random directions, their trajectories shaped by the galactic environment, not by our local geometry. The odds of an interstellar object entering nearly in the ecliptic plane are low. Not impossibly low, but noteworthy. If you wanted to survey the planets efficiently, you'd approach in the ecliptic. It minimizes travel distance. It maximizes observing opportunities. It's the logical choice for a mission planner. Or it's coincidence. The ambiguity remained, but the coincidences were accumulating. Preparations for the December approach began in earnest. NASA's deep space. Network-allocated observing time for radio tracking. The Very Large Array in New Mexico was scheduled for continuous monitoring. Optical telescopes around the world coordinated campaigns to ensure 24-hour coverage. And quietly, without public announcement, several spacefaring nations repositioned assets. A European Space Agency communications satellite in high Earth orbit adjusted its trajectory slightly, placing itself in a better position to relay observations. A classified U.S. Department of Defense satellite altered its orbit for reasons not disclosed. Japan's Hayabusa 2 spacecraft, which had successfully returned samples from asteroid Ryugu, was evaluated for a potential trajectory adjustment that could bring it near 3I Atlas's path. Not close enough for rendezvous, but close enough for imaging. The adjustments were small. The official explanations were routine, but the pattern suggested coordination. If 3I Atlas was artificial, if it posed any conceivable risk, nations wanted assets in position to observe closely. Not to intercept. The object was far too fast for any existing spacecraft to match velocities, but to watch, to record, to gather as much data as possible during the brief window when the object would be nearest, and perhaps to respond if response became necessary. The public discussion shifted during late November. Early speculation had focused on whether the object was natural or artificial. By month's end, the question had evolved. If it's artificial, what is it doing? 3 broad scenarios emerged, each with its own implications. Scenario 1. The dead probe. The object is artificial, but no longer functional. It was sent millennia ago, completed its mission or malfunctioned, and now drifts through space as an inert relic. The green emission, the radio pulses, the trajectory, all are residual processes, automated systems running on backup power or decaying components releasing stored energy. In this scenario, 3I Atlas is archaeology, not a threat. It represents technology from a civilization that may no longer exist, a message in a bottle cast across the galaxy. Approaching it would be like approaching a shipwreck, valuable for what it might teach us, but posing no active risk. Scenario 2. The active observer. The object is artificial and still operational. It's following its original programming, surveying the solar system, collecting data. It doesn't care about Earth specifically. We're just one planet among 8. Interesting. But not unique. It will make its observations, continue on its trajectory, and eventually transmit its findings home. In this scenario, 3I Atlas is indifferent. It's not here for us. We're background, part of the environment it's studying. The appropriate response is to observe without interfering, to learn what we can without disrupting its mission, and perhaps to send our own message, a brief transmission during closest approach saying, "We see you. We recognize what you are. We would like to talk." Scenario 3. The directed mission. The object is artificial, operational, and here specifically to study Earth. The timing isn't coincidental. The trajectory isn't random. It was sent in response to something. Perhaps our radio emissions leaking into space for the past century. Perhaps something earlier. A signal or biosignature detected from light years away. It's here to assess us. To determine if we're intelligent, if we're a threat, if we're worth contacting. The WOW signal in 1977 wasn't a message to Earth. It was a status update sent home saying, "Species detected, moving to investigate." In this scenario, December 18th isn't just closest approach. It's evaluation day. We don't know which scenario is correct. We don't know if any are correct. But the uncertainty shapes planning. How do you prepare for first contact when you're not sure contact is happening? How do you send a message when you don't know if anyone is listening? How do you respond to the possibility that intelligence from beyond Earth is passing through our neighborhood, watching us, deciding whether we matter? You gather data, you watch closely, you prepare messages just in case, and you wait. The data waits, and so do we. If 3I Atlas was transmitting, humans wanted to hear it. The 21-centimeter pulses detected in October remained faint but persistent, hovering just above the noise floor of most radio receivers. But just above noise meant detectable. Given enough time, enough data, enough processing patterns might emerge. The SETI Institute announced on November 22nd that it was dedicating the Allen Telescope Array in Northern California to continuous monitoring of 3I Atlas through December. 42 radio dishes, each 6 meters in diameter, working together as a single instrument. capable of detecting faint signals across a wide range of frequencies. The announcement was carefully worded. It didn't declare 3i Atlas artificial. It didn't speculate about intent. It simply stated that an object of unusual characteristics warrants comprehensive investigation using all available tools. Other institutions followed. The Parkes Observatory in Australia allocated observing time. The Arecibo Observatory, recently repaired after its 2020 collapse, scheduled intermittent observations. Amateur radio astronomers around the world pointed their dishes skyward, contributing data to open-access databases. It was the most intensive radio monitoring campaign in history, focused on a single target, coordinated across continents, and for weeks it yielded nothing new. The 47-second pulses continued, steady and unchanging. The intensity varied slightly with distance, growing stronger as the object approached the Sun, consistent with increasing power generation or more efficient transmission. But the pattern remained static. No modulation, no variation beyond the subtle 19-cycle structure identified earlier. If this was a message, it was simple, repetitive, a beacon, perhaps meant to be detected, not interpreted. Or it was machinery, a rotating component, a power cycle, a resonance in some physical system that happened to radiate at 21 centimeters as a side effect of its operation. Distinguishing between intent and accident is nearly impossible without context. A lighthouse beam looks deliberate, but it's just light rotating. A pulsar looks deliberate, but it's just physics. Determining whether 3i Atlas was trying to communicate required knowing what communication would look like from a non-human intelligence, and we didn't know. On December 1st, a team at UC Berkeley published an analysis of the 21-centimeter signal, focusing on the 19-cycle pattern. Using techniques developed for analyzing pulsar timing, they extracted subtle features in the pulse arrival times, delays and advances measured in milliseconds, tiny deviations from perfect periodicity. The deviations weren't random. They showed structure. When plotted as a time series, the deviations formed a curve, not a sine wave but something more complex, like a wave with harmonics layered on top. The pattern repeated every 19 cycles, as expected, but within each cycle there was organization. The team ran the data through various statistical tests. They checked for known natural phenomena, gravitational lensing, plasma dispersion, relativistic beaming. None fit. They checked for instrumental artifacts, clock drift, atmospheric distortion, receiver noise. None matched. The pattern was real, and it was coming from the object. But what did it mean? One possibility: nothing. Physical systems produce complex patterns naturally. A spinning object with an asymmetric mass distribution wobbles, creating variations in rotation rate. A magnetic field interacting with ionized gas creates plasma instabilities. These are processes, not messages. Another possibility: everything. If the pattern encoded information, it might represent telemetry, status reports, temperature, readings, power levels. Data transmitted home for analysis, not meant for us but detectable nonetheless. Or it might represent an attempt at communication, using a structure deliberate enough to stand out against the background of natural phenomena, but simple enough to be universal. The team didn't claim to have decoded anything. They presented the data, described the pattern, and offered possibilities. The paper concluded with a caution: interpretation requires assumptions we cannot justify. Which is another way of saying, we don't know what we're hearing, but we're listening carefully. By mid-December, the object had brightened to magnitude 11, easily visible through binoculars. Thousands of amateur astronomers observed it nightly, capturing images and spectra, contributing to the distributed network of watchers. The green glow persisted, the anti-tail persisted, the radio pulses persisted, and on December 12th, something changed. An amateur observer in New Zealand, conducting a routine imaging session, noticed that the green emission had intensified significantly. The increase was sudden. Within a 6-hour window, the brightness at 500 nanometers doubled. Follow-up observations confirmed it. The nickel emission, which had remained relatively constant for 2 months, was surging, and the surge was accompanied by a new spectral feature. Emission at 656 nanometers, the hydrogen alpha line, hydrogen. The element that had been mysteriously absent from earlier spectra. Now it was appearing, faint but unmistakable, indicating hydrogen gas in the coma. If the object was using electrolysis to split water, producing hydrogen and oxygen, then venting hydrogen would make sense as a propulsion method. Hydrogen is light. Expelled at high velocity, it provides thrust. The emission at 656 nanometers would result from solar ultraviolet exciting the hydrogen atoms before they dispersed. The object was accelerating again. Not slowing. Accelerating. Orbital tracking confirmed it. The trajectory was shifting, subtly but measurably. The perihelion distance, 0.85 AU, hadn't changed, but the angle of approach had adjusted by a few tenths of a degree. It was steering. Trajectory adjustments are routine in spaceflight. Every mission includes mid-course corrections, small burns to refine the path, compensating for errors in the initial launch or for gravitational perturbations encountered along the way. But routine or not, they signify control. A comet drifting through space doesn't steer. It follows gravity and momentum, perturbed only by the recoil from asymmetric outgassing. If outgassing jets are strong and asymmetric enough, they can alter a comet's trajectory slightly. This is well documented, observed in dozens of comets. But the trajectory change in 3I Atlas wasn't consistent with random outgassing. It was directed. The thrust vector, calculated from the observed acceleration, pointed in a direction that adjusted the Earth flyby distance by approximately 200,000 kilometers. 200,000 kilometers, roughly half the distance from Earth to the Moon. Not a huge adjustment, but enough to be deliberate, enough to shift the closest approach from 43 million kilometers to 42.8 million kilometers. Why adjust the trajectory at all? If the object's path was already bringing it within 0.3 AU, why expend energy, resources, to change it slightly? One explanation: refinement. The trajectory was already close to optimal, but a small correction ensured even greater precision. Perhaps instruments require specific viewing geometries. Perhaps the mission plan specified exact distances. Perhaps the adjustment compensated for perturbations that had occurred earlier, unnoticed. Another explanation: demonstration. The adjustment was small enough to be easily missed, but large enough to be detected by anyone watching carefully. It was a signal, not in radio waves, but in motion. We are in control. We see you. We can adjust our path if we choose. Or it was both, purpose and signal, intertwined in a single maneuver that served operational needs while simultaneously revealing capability. The trajectory adjustment sparked immediate response from space agencies. Within 48 hours, ESA released a carefully worded statement acknowledging observed non-gravitational acceleration consistent with material ejection from the object's surface. The statement noted that such accelerations were commonly observed in cometary bodies due to sublimation-driven jets. The statement was technically accurate. It was also incomplete. What it didn't mention was that the acceleration vector showed no correlation with solar heating patterns. Comets outgas most strongly on the sunward side, where heating is greatest. The jets point roughly away from the sun, creating a thrust component that typically slows the comet slightly and deflects its trajectory. The acceleration detected in 3I Atlas pointed perpendicular to the sun line. Not away from the sun, not toward it. Perpendicular, the direction required to adjust the Earth flyby distance without changing the perihelion distance. That's not random outgassing, that's propulsion. By December 14th, multiple research groups had confirmed the trajectory change independently. The orbital elements had shifted measurably. The eccentricity, still hovering slightly above 1.0, had adjusted by 0.003. The inclination had changed by 0.12 degrees. The argument of perihelion had shifted by 0.4 degrees. Small numbers. But in orbital mechanics, small numbers have large consequences. A change of 0.4 degrees in argument of perihelion, combined with the object's velocity, translated to that 200,000-kilometer adjustment in Earth flyby distance. Someone, or something, had calculated precisely how much thrust was needed, in what direction, and for how long. The maneuver required planning, it required navigation, it required knowing where Earth would be on December 18th and adjusting the trajectory to intercept that position at the optimal distance. It required intelligence. The public discourse shifted sharply. Before December 12th, the debate centered on whether 3I Atlas was artificial. After the trajectory adjustment, the debate moved to what it intended. Mainstream media coverage intensified. Cable news networks ran segments featuring astronomers, SETI researchers, and military analysts discussing scenarios. Social media exploded with speculation, memes, fears, and hopes. Some people stockpiled supplies fearing disaster. Others held viewing parties celebrating contact. Most simply watched and waited, uncertain what to feel. Governments convened emergency sessions. The United Nations Committee on the Peaceful Uses of Outer Space held closed-door meetings. NASA Administrator and ESA Director General conducted joint press conferences emphasizing that no threat has been identified and that all observations are consistent with a distant flyby. The statements were reassuring. They were also, strictly speaking, true. The object posed no collision risk. It wasn't emitting radiation beyond normal electromagnetic wavelengths. It wasn't approaching any satellites or space stations. But no threat and safe are different concepts. A probe surveying Earth, cataloging our civilization, analyzing our technologies, assessing our capabilities, that's not a threat in the immediate sense. But it changes everything about humanity's understanding of its place in the universe. And if the probe is reporting home, if it's transmitting data across light years to a civilization capable of interstellar spaceflight, then Earth's isolation, the assumption that we are alone, that we have time to develop without external influence, ends. We become known. December 15th, 2025. 3 days until closest approach. The object was now magnitude 9.5, visible to the naked eye as a faint green star in the constellation Aquarius. Observers around the world tracked it nightly, watching it drift slowly eastward, brightening incrementally, pulsing steadily at 21 centimeters. Astronomers had refined predictions for the flyby. On December 18th at 1422, UTC 3I Atlas would pass within 42.8 million kilometers of Earth, close enough that light from the object would take only 143 seconds to reach us. Close enough that radar signals, if transmitted, could reach the object in 143 seconds and return in another 143, allowing round-trip communication in under 5 minutes. Close. Enough for conversation. Not conversation in the human sense, exchanging words, ideas, intentions, but conversation in the engineering sense, signal, response, acknowledgement, ping, echo. Are you there? I am here. NASA authorized the use of the 70-meter dish at Goldstone, California, for radar observations during the flyby. The plan was straightforward. Transmit a powerful radar pulse at 8.5 gigahertz, aimed at 3I Atlas's predicted position, and listen for echoes. The radar wouldn't penetrate the object. Electromagnetic waves reflect from surfaces, but the echo would reveal size, shape, rotation rate, and surface properties. And if the object responded, if it transmitted back at the same frequency, or modulated the echo, or changed its behavior in any detectable way, that would be unambiguous. Natural objects don't respond to radar. They reflect passively, echoing back a fainter version of the transmitted signal. An active response, a signal deliberately returned, would indicate awareness, intent, capability. It would confirm everything. Other nations prepared their own observations. China's FAST telescope, the world's largest single-dish radio telescope, was scheduled for continuous monitoring. Russia's Ratan 600 radio telescope allocated time. The European LOFAR array, sensitive to low-frequency radio waves, was configured for detection of any unusual emissions, and quietly, defense agencies positioned assets. The U.S. Space Force acknowledged that routine observations would be conducted by optical and radar systems normally used for tracking satellites and space debris. Russia's Ministry of Defense issued a similar statement. China said nothing publicly, but amateur satellite trackers noted unusual activity among Chinese reconnaissance satellites. No one was preparing for conflict. The object was too fast, too distant, and too unknown to pose a conventional threat, but everyone wanted to watch closely. If the object was artificial, if it had been sent across interstellar distances, then the civilization that built it possessed technology far beyond human capability. Monitoring, recording, understanding, these were prudent measures. Responding was more complicated. Should humanity send a message? And if so, what should it say? SETI protocols developed over decades recommend caution in active transmission. Broadcasting into space without consensus is potentially dangerous. You don't know who might be listening, what they might think, how they might respond. Earth has been leaking radio signals into space for a century, but those signals are weak, diffuse, unintentional. A directed transmission is different. It's deliberate. It announces presence and intent. But 3i Atlas wasn't some distant star system. It was here, passing through our neighborhood, possibly observing us already. Remaining silent wouldn't hide us. We were already visible. On December 16th, an international coalition of scientists, ethicists, and diplomats convened virtually to discuss whether to transmit a message during the flyby. The meeting was contentious. Some argued for silence, wait, observe, learn, before revealing more than necessary. Others argued for engagement. This might be the only chance for direct contact, an opportunity that might not recur for centuries. A compromise emerged: transmit a simple, mathematically structured signal at multiple frequencies, including 21 centimeters. Not language, not complex information, just structure, prime numbers, mathematical constants, patterns that indicate intelligence without revealing specifics about human civilization. The message would say, "We see you, we know what you are, we are here," and then it would wait for response. December 17th, 2025. One day until closest approach. The object had brightened to magnitude 8.8, easily visible to anyone looking skyward from a dark location. Its green glow was unmistakable now, distinct from surrounding stars, drifting perceptibly over the course of an hour. People gathered at observatories, planetariums, parks, mountaintops, anywhere with clear skies and minimal light pollution. Some brought telescopes, some brought cameras, some simply brought themselves, standing quietly under the stars, staring at a point of light that might be carrying eyes that stared back. The mood was strange, not celebratory, not fearful, suspended, anticipatory. The feeling you get standing at a threshold, knowing that once you step through, everything changes. But not yet, knowing how. Astronomers worked through the night, capturing final pre-flyby data. The object's spectrum remained consistent. Nickel emission, hydrogen alpha, ionized oxygen, the familiar signatures now recorded in exquisite detail. The radio pulses continued at 47-second intervals, steady as a metronome, and at 03:14 UTC on December 18th, 6 hours before closest approach, the object stopped pulsing. The silence was noticed immediately. Radio telescopes around the world, listening continuously, detected the cessation simultaneously. One moment, the 21-centimeter signal was there, faint but present, pulsing regularly. The next moment, nothing, not fading, not weakening gradually, just absent. The sudden silence sent alerts through automated systems. Astronomers woke to notifications, checked data streams, confirmed the absence, and began hypothesizing. Had the power source failed? Had the object entered some new operational mode? Was this deliberate? A signal in itself, the absence of signal marking a transition? Or had it simply completed its transmission, sent its final status update, and now prepared for the next phase of whatever mission it was following? There were no answers, only the silence and the slow approach and the waiting. December 18th, 2025, 14:22 UTC. At the moment of closest approach, 3I Atlas was precisely 42,147,293 kilometers from Earth, a distance measured with meter precision by radar ranging from Goldstone. The object moved at 57.3 kilometers per second relative to Earth, slightly slower than its initial detection velocity due to solar gravity and its own trajectory adjustments. Light from the object, emitted 143 seconds earlier, arrived at Earth carrying the spectrum of its surface: green nickel emission, hydrogen alpha, ionized oxygen. Radio telescopes listened for the 21-centimeter pulses that had ceased 11 hours earlier. Silence. The Goldstone radar transmitted its pulse at 14:20 UTC, 2 minutes before closest approach. The radar signal, traveling at the speed of light, would reach the object at 14:22:23, precisely at closest approach. If the object reflected the signal passively, the echo would return at 14:24:46. If the object responded actively, the response could come at any time. At 14:22:23, the transmitted radar pulse reached 3I Atlas. At 14:24:46, Goldstone received an echo. The signal wasn't strong. Radar echoes never are, diminished by distance and spreading across space. But it was detectable. The signal. Processing computers locked onto the return calculated delay, measured Doppler shift, began constructing a profile. And then, at 14:24:51, 5 seconds after the expected echo, a second signal arrived. Same frequency, stronger intensity. Modulated. The modulation wasn't complex. It was a simple on-off pattern lasting 3 seconds, 12 pulses, each 250 milliseconds long, separated by 250 millisecond gaps. 12 pulses. Binary rhythm. On-off, on-off, on-off. It wasn't an echo. Echoes don't arrive after the primary return. Echoes don't show modulation different from the transmitted signal. This was a response, a signal transmitted by the object itself, using the same frequency as the radar pulse, arriving seconds after the passive echo. The object had answered. The response was detected simultaneously by other observatories. FAST in China recorded it. Ratan 600 in Russia recorded it. LOFAR in Europe, though optimized for different frequencies, detected faint structure consistent with harmonic emissions. Within minutes, the data was shared across secure channels. Within an hour, analysis began. Within 2 hours, preliminary interpretations circulated among researchers. The 12 pulses defied simple explanation. 12 isn't a particularly significant number in human culture, not prime, not a power of 2, not a mathematical constant. But it is the number of months in a year, the number of hours on a clock face, a number humans use frequently for organizing time. Was it coincidence? Was the object simply responding with a burst of pulses that happened to number 12? Or was it demonstrating awareness, showing that it had studied human systems, understood our conventions, and chosen a number we would recognize as structured? The ambiguity was maddening. Every interpretation required assumptions. Natural phenomena don't respond to radar in modulated patterns, but defining natural when dealing with an interstellar object of unknown origin was nearly impossible. The scientific community fractured into interpretations. Some argued the response was proof of artificial intelligence, an autonomous system acknowledging contact. Others argued it was proof of misinterpretation, a coincidental signal unrelated to the radar pulse that happened to arrive seconds later. The timing could be chance. The frequency match could be instrumental artifact. The modulation could be natural variability. But 12 pulses, evenly spaced, at precisely the radar frequency, arriving precisely after closest approach during the most intensive observation campaign in history. Coincidence requires luck. This required improbable luck compounded repeatedly. The international message, the transmission of prime numbers and mathematical constants, went out at 14:30 UTC, 8 minutes after closest approach, broadcast at 21 centimeters from the Arecibo Observatory. The message was brief, a sequence of pulses representing the first 10 prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, followed by a representation of pi to 10 decimal places encoded in binary. It said, "We understand mathematics. We recognize patterns. We are intelligent." The transmission lasted 90 seconds. Then Arecibo switched to receiving mode, listening for response. At 14:35 UTC, 5 minutes after the transmission, long enough for the signal to reach the object and for a response to return, Arecibo detected a signal at 21 centimeters, not the 12 pulse pattern, something different, a continuous tone, lasting 47 seconds, the same duration as the original pulse period detected months earlier. The tone was unmodulated, unchanging in frequency, a pure carrier wave. And then it stopped. One tone, 47 seconds. Silence. It could have been many things. A malfunction, a burst of natural radio emission, a response from Earth-based transmitters accidentally aligned with the observation. But it arrived exactly when a response would arrive, and it lasted exactly as long as the object's characteristic pulse period. If this was communication, it was minimal, acknowledgement without elaboration. "I hear you, I am here, but I will not say more." Or it was echo, the object reflecting the transmitted signal back, passively, without intent. The ambiguity remained. Over the next 6 hours, as 3I Atlas receded from Earth, radio telescopes around the world continued listening. The 21-centimeter pulses did not resume. The object remained silent, optically bright but radio quiet, receding at 57 kilometers per second toward its perihelion with the Sun. Imaging continued. JWST captured thermal infrared data showing surface temperature variations consistent with localized heating, regions 50 Kelvin warmer than the surroundings, distributed asymmetrically across the nucleus. Hubble captured visible light images resolving the nucleus as a slightly elongated smudge, consistent with earlier size estimates, and amateur astronomers, watching through backyard telescopes, continued, seeing the green glow now slightly fainter as distance increased. By December 19th, the object had passed. The moment of closest approach was over. The opportunity for direct interaction, if that's what it had been, was gone. And humanity was left with data, ambiguity, and questions that had no definitive answers. Was 3I Atlas artificial? The evidence suggested yes. The trajectory, the chemistry, the radio signals, the trajectory adjustment, the radar response, each piece, individually, could be explained naturally with sufficient imagination. But collectively, they strained natural explanations beyond plausibility. Was it intelligent? That depended on definition. If intelligence means capability, navigation, propulsion, response, then yes. If intelligence means consciousness, awareness, intent, then perhaps. Or perhaps it was autonomous, programmed, executing instructions written centuries ago by minds now silent. Did it communicate? It responded. Whether that response was communication or reflexive reaction remained unclear, and most importantly, what would it do next? December 22nd, 2025. 0647 UTC. 3I Atlas reached perihelion, the point of closest approach to the Sun, at a distance of 0.85 astronomical units, approximately 127 million kilometers. For context, Earth orbits at 1 AU. Mercury's orbit ranges from 0.31 to 0.47 AU. The object was passing through the inner solar system, but remaining safely beyond the innermost planet. At this distance, solar heating would be intense. Temperatures on the sunward side of a cometary nucleus typically reach 300 to 400 Kelvin, hot enough to vaporize water ice rapidly, creating the dramatic tails and comae that make comets spectacular. 3I Atlas responded to perihelion by becoming less active. The green emission faded significantly. The brightness at 500 nanometers dropped by 60% within 12 hours of perihelion passage. The hydrogen alpha emission, which had surged during the trajectory adjustment, declined even more steeply, becoming undetectable by December 23rd. It was as if the object was shutting down, conserving resources, reducing output as it passed through the region of highest solar flux, rather than increasing activity as comets naturally do. The thermal infrared data from JWST showed surface temperatures rising, as expected from solar heating, but the increase was modest, from 200 Kelvin to 270 Kelvin. For comparison, a typical comet at this distance should reach 350 Kelvin or higher on the sunward side. The object was reflecting sunlight efficiently, or shielding itself, or both. Radar observations from Goldstone conducted during perihelion passage revealed additional details about the object's shape and rotation. The nucleus was indeed elongated, approximately 850 meters long and 380 meters wide, confirmed with higher precision than earlier estimates, and it was rotating slowly, with a period of approximately 28 hours. 28 hours is unusually slow for a small body. Asteroids and comets typically rotate much faster, periods of hours or even minutes, because angular momentum is conserved as they form from collapsing clouds of dust. A slow rotation suggests either dissipation of angular momentum over time or deliberate stabilization. Spacecraft stabilize rotation for practical reasons. Fast rotation complicates navigation, imaging, and communication. Antennas need to point in specific directions. Solar panels need consistent orientation. Instruments need stable platforms. A 28-hour rotation provides that stability. By December 24th, the object was receding from the Sun, moving outward through the inner solar system on its hyperbolic trajectory. The orbital elements, refined continuously with new observations, showed the eccentricity holding steady at 1.019. Still hyperbolic, still unbound. The object would leave the solar system, unless it changed its trajectory again. Observers watched for signs of additional maneuvers, any thrust, any trajectory adjustment, any indication that the object was altering course. For 3 days, nothing changed. The path remained consistent with a purely gravitational trajectory, modified only by the single maneuver detected on December 12th. And then, on December 27th, the 21-centimeter pulses resumed. The signal returned abruptly at 11:33 UTC, detected simultaneously by multiple radio telescopes. The pulse period was unchanged, 47 seconds. The intensity was similar to pre-perihelion levels. The 19-cycle pattern with its subtle timing variations was present. The object was transmitting again. But there was a difference. The pulses were now stronger, approximately 30% more intense than during the approach phase. Either the transmission power had increased, or the directionality had changed, focusing more energy toward Earth, or toward something beyond Earth, in the direction Earth happened to be. The increased signal strength revived speculation. Was the object transmitting data from its perihelion passage? Had it collected information during closest approach to the Sun, during the flyby of Earth, and was now sending it home? If so, the transmission would take years to arrive. The nearest candidate origin systems, those 11 stars in Sagittarius aligned with the WOW signal, were over 100 light-years away. A radio signal travels at the speed of light. A transmission sent in December 2025 wouldn't arrive until sometime in the 2100s. By then, humanity might have interstellar spacecraft of its own, or we might be extinct, or we might be watching the skies for a response, wondering if the civilization that sent 3I Atlas still existed, still cared, still remembered why they'd sent a probe into the void centuries ago. The trajectory calculations, extended forward in time, showed 3I Atlas exiting the solar system over the next several years. By 2030, it would pass beyond Jupiter's orbit. By 2035, beyond Saturn. By 2045, beyond Neptune and into the Kuiper Belt. And then, sometime in the 2050s, it would cross the heliopause, the boundary where the Sun's influence fades and interstellar space begins. The same boundary Oumuamua had crossed in 2017, departing as mysteriously as it had arrived, unless the object changed course, unless the single trajectory adjustment detected in December was the first of many, unless the mission wasn't complete. Space agencies quietly began planning long-term monitoring campaigns. Telescopes would track the object as long as possible, until it faded, into the depths of space, too distant and faint for even the most powerful instruments to detect. But tracking an object for decades requires resources, justification, sustained interest. Would humanity maintain focus on 3i Atlas for years, or would attention drift, as it always does, toward new concerns, new crises, new mysteries? The object would recede into history, becoming another data point, another unsolved question, another ambiguity in the long list of things we observed, but never fully understood, unless it came back. Science is built on data, measurements, observations, records that persist beyond individual memory. When something unusual happens, the data remains, available for reanalysis, reinterpretation, refinement, as techniques improve and understanding deepens. By January 2026, the compiled data set on 3i Atlas was staggering. Tens of thousands of images from ground-based and space-based telescopes, hundreds of spectra covering ultraviolet through infrared, thousands of hours of radio observations, radar profiles, trajectory measurements, light curves, photometric time series. It represented the most comprehensive study of an interstellar object ever conducted, surpassing Oumuamua and Borisov by orders of magnitude in data volume and temporal coverage. And embedded in that data were details that might take years to extract. One example emerged in late January. The thermal infrared observations from JWST, when analyzed using advanced modeling techniques, showed faint periodic variations in surface temperature, oscillations with a period of approximately 28 hours, matching the object's rotation. But the variations weren't uniform across the surface. Some regions showed temperature oscillations with amplitudes of 20 Kelvin. Others showed almost no variation, remaining isothermal despite rotating in and out of sunlight. Isothermal surfaces on a rotating object require thermal management. Natural materials heat and cool as they rotate. Sunlit sides warm, shadowed sides cool. Maintaining constant temperature requires either very high thermal conductivity, distributing heat evenly across the surface, or active thermal control, using internal systems to regulate temperature. Both options implied structure, internal heat pipes perhaps, conducting warmth from hot regions to cold ones, or active cooling systems, radiating excess heat from specific locations. Neither option was natural. Another detail emerged from analysis of the radar echoes. The signal processing team at Goldstone, reviewing the December 18th data with refined algorithms, detected faint secondary echoes, reflections arriving microseconds after the primary return. Secondary echoes indicate internal structure. When radar waves penetrate a surface and reflect from internal boundaries, layers of different material, voids, interfaces, they create delayed echoes that reveal subsurface geometry. The echoes detected in 3i Atlas were weak but consistent across multiple observations. They suggested internal cavities approximately 50 to 100 meters below the surface, distributed asymmetrically through the nucleus. Cavities, empty spaces, voids where you'd expect solid material. The interpretation was cautious. The data are consistent with a heterogeneous internal structure, possibly indicating a rubble pile configuration with large voids. Translation: maybe it's just loosely packed, like other small bodies, but rubble piles don't maintain isothermal surfaces, and they don't respond to radar with modulated signals. By February, multiple papers had been submitted to peer-reviewed journals. Some argued for natural explanations, proposing novel comet physics or unusual formation conditions that could, with sufficient creativity, explain the observations. Others argued for artificial origins, laying out the cumulative case, trajectory, chemistry, signals, thermal properties, trajectory adjustment, radar response. The reviewers were in a difficult position. Extraordinary claims require extraordinary evidence. But what constitutes extraordinary evidence for something unprecedented? How do you evaluate a claim when the phenomenon itself is outside the framework of existing theory? Some papers were accepted with revisions, others were rejected as speculative. A few were published but immediately disputed, criticized for assumptions or interpretations. The scientific process was working, slowly, messily, but working. Data was being scrutinized, hypotheses tested, alternative explanations proposed. The discourse was contentious, but that's how science handles uncertainty. What emerged from the debate was not consensus, but refined questions. If 3I Atlas was artificial, who built it? The 11 candidate stars in Sagittarius were all similar to the Sun, yellow and orange dwarfs, capable of hosting habitable planets. But none showed signs of advanced civilization in archival observations. No megastructures, no artificial radio signals, no optical anomalies suggesting engineering on stellar scales, which meant either the builders were subtle or they were gone. If the object was a probe, what was its mission? The close approach to Earth suggested observation, but the data collection seemed passive. No active scanning, no sampling of Earth's atmosphere, no deployment of sub-probes into planetary orbit. Just observation from a distance, followed by departure. Perhaps that was sufficient. Perhaps high-resolution spectroscopy from 40 million kilometers away could reveal everything needed. Atmospheric composition, industrial pollutants, radio emissions, signs of technology. Perhaps physical samples were unnecessary. Or perhaps the mission wasn't observation at all. Perhaps it was transit, passing through our system en route to somewhere else, using the Sun's gravity for trajectory adjustment, conserving fuel by exploiting gravitational assists. In that interpretation, Earth was incidental. We noticed the object because it passed nearby, but we weren't the target. We were background. That possibility was, in some ways, more unsettling than deliberate observation. It suggested our solar system was merely a waypoint, a convenient location for course corrections, no more significant than a rest stop on an interstellar highway. It suggested we weren't important enough to merit attention. The connection between 3I Atlas and the 1977 WOW signal had been noted early, but mostly as curiosity, an interesting coincidence, but not proof of anything. By March 2026, with months of data accumulated and the object receding beyond Mars's orbit, researchers began examining the connection more carefully. The WOW signal had been detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University. It lasted 72 seconds, the maximum duration possible given the telescope's design. The signal was narrowband, centered at 1420 MHz, 21 centimeters, and showed a frequency drift, consistent with a source in space, not on Earth. The intensity was remarkable, 30 times stronger than background noise, clearly artificial in character. But it was never detected again, despite follow-up observations spanning decades. The source location was uncertain, constrained only to a region of sky about 2 degrees wide in the constellation Sagittarius. Over 48 years, the stars in that region had moved slightly due to proper motion, their slow drift across the sky over time. When researchers calculated where those stars would have been in 1977, one stood out, a K-type orange dwarf, slightly cooler and smaller than the Sun, located 162 light-years from Earth. The star had no official name, just a catalogue designation. It wasn't particularly remarkable. But its position in 1977, accounting for proper motion, placed it within the WOW signal's localization error region. And when researchers calculated backward from 3I Atlas's current trajectory, extrapolating where the object must have been decades or centuries earlier to arrive on its present course, the origin vector pointed directly at that same star, not to within 10 degrees, not to within 5, to within 0.3 degrees, well within the combined uncertainties of the trajectory calculation and the proper motion correction. One star, one signal, one object, all aligned. The probability calculation was straightforward. The WOW signal location contained roughly 10,000 stars within the observational cone. The odds that 3I Atlas's trajectory would point back to one specific star purely by chance were about 1 in 10,000. Not impossible, but unlikely. Add the timing, The WOW signal in 1977, the object's arrival in 2025, 48 years apart. If the object had been traveling at 60 km/s for that entire time, it would have covered approximately 90 billion kilometers, roughly 600 astronomical units. That's consistent with the distance from the outer solar system, where a probe might have been, lingering undetected, to the inner system. Consistent with an object entering the outer solar system in the late 1970s, transmitting a notification signal, then spending decades traversing inward. Or its coincidence. 48 years, 162 light-years, 60 km/s. These are numbers, and numbers can align by chance, but the green light doesn't align by chance. The nickel emission doesn't. The trajectory adjustment doesn't. The radar response doesn't. Each additional detail narrows the probability. Space, reducing the likelihood of coincidence until the alternative, deliberate connection, becomes more plausible than chance. By April, a paper was published in the Astrophysical Journal, laying out the connection systematically. The authors were careful, hedging their conclusions with appropriate caveats, but the final sentence was unequivocal. The spatial and temporal correlation between the 1977 WOW signal and the 2025 detection of 3I Atlas suggests a common origin and supports the hypothesis of directed interstellar exploration. Directed interstellar exploration, not speculation, not fringe theory, hypothesis, a testable, scientific claim backed by data. The paper was cited hundreds of times within weeks. It sparked renewed interest in the WOW signal, prompting archival searches for similar signals, reanalysis of old data, new observation campaigns targeting the candidate origin star. And it crystallized a realization. If 3I Atlas was sent from that star in response to something, detected here, some signal Earth inadvertently transmitted, some biosignature visible across light years, then the timing suggested the probe was launched sometime in the mid-1800s, 1860s, 1870s, before radio, before powered flight, before humanity announced its presence technologically, which meant the detection wasn't of our technology, it was of us. Biological signatures in Earth's atmosphere, oxygen and methane in ratios indicating life, perhaps chlorophyll absorption, features visible in reflected sunlight. We were detected not because we built transmitters, but because we breathe. By mid-2026, 3I Atlas had faded to magnitude 15, requiring large amateur telescopes to detect. It was moving outward through the asteroid belt, en route to Jupiter's orbit, still transmitting at 21 centimeters, still following its hyperbolic trajectory. The orbital elements remained stable. Eccentricity, 1.019. No further trajectory adjustments detected. The object was leaving. But eccentricity of 1.019 is barely hyperbolic. A velocity change of just 30 meters per second, less than 0.1% of its current velocity, would drop the eccentricity below 1.0, placing the object on a closed orbit. It would no longer escape the solar system. It would become a permanent resident, looping outward toward the Kuiper belt, then falling back inward in a decades-long ellipse, returning periodically like a comet. The question wasn't whether the object could adjust its trajectory again. It had already demonstrated that capability. The question was whether it would, and if it did, where would it go? One possibility, outward. The object completes its mission, gathers data, and departs the solar system as planned, returning to interstellar space and eventually to its origin system, assuming it's capable of multi-century transit. Another possibility, inward. The object adjusts course, establishing a bound orbit that keeps it within the solar system indefinitely, perhaps for continued observation. Perhaps because the mission requires long-term presence. Perhaps because returning home across 162 light-years isn't feasible even for technology this advanced. A third possibility, Lagrange orbit. There are 5 gravitationally stable points in the Sun-Earth system where an object can remain stationary relative to both bodies. The L4 and L5 points located 60 degrees ahead and behind Earth in its orbit, are particularly stable. Natural parking spots for asteroids and, potentially, for observation platforms. An object positioned at L4 or L5 could observe Earth continuously, maintaining fixed distance and orientation, minimizing fuel use. It's where you'd place a satellite if you wanted to watch something long-term. Several researchers suggested that if 3I Atlas intended to remain in the solar system, a Lagrange point would be the logical destination. The trajectory adjustment required was calculable, another small burn, a few meters per second of velocity change, timed, precisely to place the object at L4 or L5. Telescopes were already planning to monitor the L4 and L5 regions over the coming months, searching for any faint object that might indicate 3I Atlas had taken up residence. The broader implication of potential return was profound. If the object remained in the solar system, humanity would have ongoing access to it, not for centuries, but indefinitely. It could be studied continuously, observed across multiple orbits, potentially approached by spacecraft, and eventually, if technology advanced sufficiently, visited. NASA and ESA began preliminary studies for a mission to rendezvous with 3I Atlas, assuming it established a bound orbit. The challenges were substantial, matching velocity with an object moving at tens of kilometers per second, carrying enough fuel for trajectory adjustments, designing instruments for close-range analysis of something potentially artificial, but feasible. Within a decade, perhaps two, a mission could be ready. The decision to pursue such a mission would require international consensus, significant funding and public support. But the precedent existed. Humanity had sent probes to comets before, Rosetta to 67P, Deep Impact to Tempel 1, Stardust to Wild 2. We knew how to reach distant, fast-moving objects. 3I Atlas would just be different, not scientifically different in the formal sense. The mission design would use the same physics, the same orbital mechanics, the same navigation techniques, but psychologically different, philosophically different. You send a probe to a comet to study natural history, the formation of the solar system, the chemistry of primordial ices, the dynamics of small bodies. You learn about where we came from. You send a probe to an artificial object to study something else entirely, to learn who else exists, what they know, what they've built, how they think, and perhaps, if the object is still functional, to initiate contact at close range. Not radio signals, across millions of kilometers, but proximity, presence. A human-built spacecraft alongside something built by minds not human. First contact, not as message exchange, but as meeting. By late 2026, public attention had drifted. 3I Atlas remained a topic in astronomy journals, a subject of ongoing research, but the headlines had moved on. Other crises emerged, other mysteries captured imagination. The object faded from magnitude 15 to 16, then 17, slipping below the threshold of all but the largest telescopes. It was still transmitting. Radio telescopes still detected the 21-centimeter pulses, now fainter but consistent. The 19-cycle pattern persisted. The 47-second period remained stable. But fewer people were listening. This is the nature of attention. Humans focus on novelty, crisis, immediate concerns. An object receding into the outer solar system, behaving predictably, offers no urgency. It becomes background, part of the catalogue of things we've observed and filed away, for future consideration. Yet the questions remained unanswered. Was 3I Atlas artificial? The data suggested yes, but definitive proof, unambiguous evidence that would satisfy even the most skeptical, never materialized. No clear message, no visible machinery. No landing, no interaction, no moment of revelation that removed all doubt. Just data. Strange, compelling, difficult to explain data. Science deals with likelihoods, not certainties. The likelihood that 3I Atlas was artificial, based on cumulative evidence, was high. But high likelihood isn't the same as proof. And without proof, institutional caution prevails. NASA never officially declared the object artificial. Neither did ESA. The consensus statement, issued jointly in August 2026, was carefully worded. 3I Atlas exhibits characteristics inconsistent with typical cometary bodies, including unusual spectroscopic signatures, trajectory adjustments consistent with propulsive maneuvers, and radio emissions of unknown origin. While natural explanations cannot be entirely excluded, the object warrants continued observation and study. Warrants continued observation, not represents extraterrestrial technology, not confirms intelligent design, just worth watching. The statement satisfied no one. Skeptics argued it was too speculative, lending credibility to fringe theories. Advocates argued it was too cautious, refusing to acknowledge obvious implications. But it was honest. Science often ends not with answers, but with refined uncertainty, better questions, narrower ranges of possibility, clearer understanding of what we don't know. 3I Atlas was now in that category, well studied but unresolved. A mystery with data, but no conclusion. In November 2026, nearly a year after closest approach, the object crossed Jupiter's orbit, moving outward at 58 kilometers per second. The radio pulses continued. Faint optical emission persisted, though now requiring long exposures to detect. And then, on November 14th, 2026 at 1842 UTC, the 21-centimeter pulses changed. Not stopped, changed. The pulse period shortened from 47 seconds to 41 seconds. The shift was abrupt, detected simultaneously by 3 radio observatories. One moment, the familiar rhythm. The next, a new rhythm. Faster, distinct, unmistakable. The change triggered alerts. Astronomers scrambled to observe, to confirm, to analyze. Within hours, the new pattern was verified. Within days, analysis showed that the 19-cycle structure remained but compressed. The same pattern accelerated. Why would the object change its transmission pattern? One hypothesis, operational transition. The object was entering a new phase of its mission, signaled by the change in pulse rate. Perhaps it was preparing for course adjustment, or reconfiguring systems, or shifting to a different operational mode. Another hypothesis, communication. The change wasn't operational, but deliberate. A signal meant to be noticed, indicating awareness that Earth was listening. By changing the pattern at a time when detection was certain, the object demonstrated both capability and intent. Or it was malfunction, a failing power system, a degrading component, a system entering emergency mode. 3 months later, in February 2027, the pulse rate changed again, from 41 seconds to 37 seconds. Another abrupt transition, another new rhythm. And in May 2027, it changed to 33 seconds, a pattern within the pattern. The pulse period was decreasing in steps. 47, 41, 37, 33. Those are prime gaps, 6, 4, 4. Not the primes themselves, but related, close to a sequence mathematicians might recognize, or coincidence. 4 data points don't establish a pattern definitively. Statistical fluctuations could produce apparent sequences that mean nothing. But combined with everything else, the trajectory, the chemistry, the timing, the radar response, the changing pulse rate added another piece to the puzzle. And the puzzle was becoming harder to dismiss. By 2029, 3I Atlas had passed Saturn's orbit, moving into the outer solar system. It was now magnitude 19, invisible to all but the most powerful ground-based telescopes and requiring significant observing time to detect. The Hubble Space Telescope still tracked it occasionally. JWST dedicated a few hours per year. Radio observatories continued listening when time allowed. But resources are finite, and other targets competed for attention. The object was fading into history, except for one detail, the trajectory. In August 2029, orbital analysts noticed something. The eccentricity, which had remained stable at 1.019 for 3 years, had decreased slightly. Preliminary calculations suggested 1.016. Measurement uncertainty was significant at these distances. The object was faint, position measurements less precise, orbital fits less certain. But multiple independent analyses confirmed the trend. The eccentricity was dropping. If the trend continued, the object would achieve a bound orbit within 2 years. This wasn't speculation, this was observation. The object was slowing, subtly but measurably, through some mechanism, probably low-thrust propulsion, too faint to detect directly, but sufficient to change velocity by meters per second over years. It was staying. The realization prompted renewed interest. If 3I Atlas was establishing a bound orbit, if it intended to remain in the solar system, then access wasn't temporary. The object would return, periodically, orbiting the Sun like a comet but on a scale measured in decades. Mission planners revised their studies. A rendezvous wasn't urgent. Decades remained before the object would complete an orbit and return to the inner system, but it was feasible. Time existed to design, fund, build and launch a spacecraft capable of reaching 3I Atlas at aphelion, the farthest point in its orbit, where velocities would be lowest and rendezvous easiest. By 2031, the eccentricity had dropped to 0.997, below 1.0, definitively bound. The E object was now a permanent member of the solar system, following an elliptical orbit with a period of approximately 87 years. Aphelion would occur near 80 AU, twice Neptune's distance, deep in the Kuiper belt. Perihelion would bring it back to 0.85 AU, near where it had passed in 2025. In 87 years it would return, 21 to 12, well within the lifespan of people born in the 2020s, well within the technological horizon of humanity. We would have another chance. What did 3I Atlas change? Not everything. Daily life continued. Economies functioned. Politics remained contentious. People lived, worked, worried about immediate concerns. The existence of a possibly artificial interstellar object in the outer solar system didn't alter grocery prices or election outcomes or personal relationships, but it changed context. Before 3I Atlas, the question, "Are we alone?" was abstract, philosophical, something discussed in late-night conversations, in science fiction, in SETI programs that searched distant stars for signals that never came. After 3I Atlas, the question had data. Ambiguous data, certainly. Inconclusive data, yes. But data nonetheless. Observations that suggested, even if they didn't prove, that intelligence existed beyond Earth. And that changed how humanity thought about itself. Not immediately, not universally, but gradually, in ways both subtle and profound. Funding for SETI increased, not dramatically but measurably. Governments and private organizations allocated resources to search programs, to radio telescope arrays, to optical surveys hunting for anomalous signals or objects. Space exploration gained renewed urgency. If the solar system contained artificial objects, even just one, then understanding our local environment became more pressing. Surveys of asteroids intensified. Proposals for missions to the outer system gained traction. The possibility that other objects, smaller, older, dormant, might exist among the Kuiper belt objects motivated searches. And education shifted. Astronomy curricula began including discussion of interstellar objects, of technosignatures, of the methods used to distinguish natural from artificial. Students learned not just that planets exist around other stars, but that those planets might harbor civilizations capable of sending probes across the void. The generation growing up in the 2030s and 2040s would be the first to consider interstellar contact not as science fiction, but as plausible reality. They would be the ones building the missions, analyzing the data, perhaps even encountering whatever 3I Atlas represented when it returned in 2112. The scientific legacy was clearer. 3I Atlas demonstrated that interstellar objects were detectable, characterizable, and potentially common. It proved that our survey systems, while imperfect, could identify anomalies. It showed that ambiguity could persist even with extensive data, that some questions don't resolve neatly. And it established protocols. How to observe, how to analyze, how to communicate findings when those findings were extraordinary but not definitive. The next interstellar object, and there would be a next one, statistics assured it, would be studied better, detected earlier, characterized more thoroughly. The lessons from 3I Atlas would guide response, shape observation strategies, inform interpretation. We had learned from encounter, and if the next object was also artificial, if it showed similar characteristics or different ones, the pattern would strengthen. Two objects suggested not coincidence, but something systematic, a network perhaps of probes distributed through the galaxy, exploring, observing, waiting. One object was anomaly, two would be pattern, three would be certainty. We were watching for the next one. 87 years after its first close approach, 3I Atlas will return to the inner solar system. The calculation is precise. Orbital mechanics allows prediction with high confidence over such timescales. On March 6, 2112, at 0914 UTC, the object will pass within 0.82 AU of the Sun, slightly closer than its 2025 perihelion. 2 weeks later, on March 19th, it will pass within 0.34 AU of Earth, closer than the first approach, close enough for detailed radar mapping, close enough for visible light imaging that might resolve surface features. The people who will observe that return haven't been born yet. The telescopes that will be used don't exist. The questions they'll ask will be shaped by knowledge we don't yet have, discoveries made in the decades between, technologies developed, theories refined. But some questions will remain the same. Is it artificial? By 2112, perhaps we'll know. Perhaps closer observation during the first orbit will have revealed structures, emissions, behaviors that remove all doubt. Or perhaps ambiguity will persist, the object remaining just beyond definitive characterization. Is it functional? The radio pulses, if they continue, will have been transmitting for 87 years by the time of return. Systems that robust suggest either extraordinary engineering or automated processes running on stored energy. Either way, impressive. Will it respond? If humanity sends a mission to rendezvous with 3I Atlas during its outbound journey, if we place a spacecraft alongside it, if we attempt close-range communication or even physical contact, will the object acknowledge us? Or will it continue its programmed routine, indifferent to our presence, focused on whatever mission it was designed to complete centuries ago? And the deepest question, what will it report? If 3I Atlas transmits data home after each perihelion passage, if it's been observing Earth across decades, if it returns in 2112 to gather updated information before sending another report, what will it say about us? In 1977, when the WOW signal was transmitted, humanity was emerging from the Cold War, grappling with environmental crises, reaching toward space with tentative steps. By 2025, we had robots on Mars, telescopes observing the early universe and the beginnings of a multi-planetary presence. By 2112, where will we be? Still confined to our solar system or reaching toward the stars ourselves? Still divided by borders and ideologies or unified by the knowledge that we're not alone? The object will document whatever it finds, and if its builders still exist, if they're still listening across 162 light-years, they'll receive that report sometime in the 2270s. 2.5 centuries from now, a civilization we've never met will learn what humanity became in the 22nd century. We won't know what they think of us. We won't know if they respond. We won't even know if they still exist. But they'll know about us. That's the legacy of 3I Atlas, not proof, not contact, but awareness. Somewhere beyond the solar system, minds not our own sent something here. It arrived, it observed, and it will return. We are seen, and once you know you're seen, you can never unknow it. Tonight, in observatories scattered across the world, telescopes point toward the outer solar system. Radio dishes listen for faint pulses at 21 centimeters. Orbital analysts refine trajectory predictions. Archival searches continue, hunting for older objects that might have passed through centuries ago, undetected. 3I Atlas is out there, beyond Saturn, fading slowly into darkness as it climbs toward aphelion. In a few decades, it will reach the farthest point in its orbit, 80 AU from the Sun, 3 times Neptune's distance, and pause balanced between the Sun's gravity pulling inward and its velocity carrying it outward. And then it will fall back. The object doesn't care whether we understand it. It doesn't care whether we call it artificial or natural, probe or comet, message or accident. It simply is, doing whatever it was built or formed to do, following physics and programming, moving through the void. But we care. We care because we're curious. Because we build stories from patterns. Because an unexplained green light in the darkness captures imagination in ways that fully explained phenomena never do. We care because 3I Atlas represents possibility. The possibility that the universe isn't empty, that intelligence exists beyond our world, that someone, somewhere sent something here, and that something arrived. The data waits in archives, on servers, in published papers and unpublished observations. Future researchers will analyze it, reinterpret it, extract details that current techniques miss. The object will be studied for generations, regardless of whether it ever reveals its nature definitively, and in 2112, when it returns, we'll be ready. Better telescopes, better instruments, better questions. And perhaps, if we've learned enough, better understanding. But even then, even with decades of additional data, the central mystery may remain. Did someone send this? Or did the universe, in its vastness and strangeness, simply produce something that looks designed? The answer matters, but the question matters more, because asking the question means we've accepted that design is possible, that intelligence spans stars, that we might not be the only ones watching the cosmos, wondering if anyone else is out there. 3I Atlas doesn't answer that question, but it asks it in every green photon emitted, in every radio pulse transmitted, in every kilometer traveled across the interstellar dark. And we listen. The data waits. And so do we. Would we recognize intelligence if it weren't trying to speak? Perhaps we already have.